Welcome to the ARE Kaplan practice test example number 9, and they want you to find the centroid of this section right here. And what we're going to do as well, it's kind of hard to see the section, but if you want to go ahead and look, there's this right here, and this is the web, and then you have another flange over here. And you want to find the centroid of this, and what the centroid is the center point of the area, if that makes any sense. And in addition, I'm going to go ahead and find the moment of inertia, which is commonly called out as I. And what that is, it's pretty much, without using too many technical terms, is the ability of a shape to resist moment. For instance, so it's the more moment of inertia you have, the more further away from the axis you are, the more mass or area you have away from the axis. For instance, these two sections could have the exact same moment. This section, or not moment, but area. This section and this section is a little bit wider. These could have the exact same area. For instance, if it looks like this, overlaid it, if you overlaid that on top, it would look like that, but the I section would have more moment of inertia because more of the area is away from the neutral axis. And there's a neutral axis. That means pretty much this is the center of the area. Alright, I'm going to back up. Alright, and the equation for the centroid, or I would call where the neutral axis is of a section, is you want to take this sum of the areas times distance. And I'm going to go ahead and do this, put this in here. The sum of the areas times distance over the sums of the areas. So friends, what you want to do is, to solve this, is break it up into blocks. I'm going to call this area 1. This from right here to right here will be area 2. We'll call it A2. And this area right here, this bottom flange, will be area 3. In the example, he wants you to go from the top down is the way they do it. You could do from the bottom up. It just kind of depends which way you want to. Typically I'll go from the bottom up, and most engineering practice, that's where the centroid is measured from. But anyways, he wants you to do it from the top down in this book, the example, so that's what we'll do. We could also go from the bottom up to double check it if we have enough time. We'll see. So you want to take the sums of the area times the distance. So you want to take the area of A1 times the distance of the centroid. I hope I didn't really mention that before. The distance to the centroid. And hopefully you know that the centroid is this of a rectangle is halfway. So anyways, you have the area. Let's go down here. Okay, Y. And then you have, let's just draw a big old line. Usually this takes up a lot of room. So you have 4 inches times 10 inches is the area. So 4 inch times 10 inch. And you want to do the distance to the centroid. Remember, distance to the centroid. So 4, and the center of that rectangle right there is halfway down, obviously. So it's 2 inches to the centroid. So we want to go 4 times 10 times 2. And that's A1. Let's just say that's A1, just to let you know. Plus, we're going to go A2, which is 1 inch wide times 6 inches tall. And then halfway right here is the neutral axis, or we'll call it not the neutral axis, but the centroid of this rectangle right here. So, well, let's go ahead and change colors actually. And we'll go ahead and say 1 inch 6 inches. That's 1 inch right there. This is 6 inches. And remember, it's what is the distance from the bottom or top? We're saying from exit originally is this. It's 3 inches to the top there, but then you have to add these other 4 inches, so it's 7 inches for A2. And then let's go ahead and go to A3. We'll do that in ugly gold or whatever that is, A3. And then you add 6 inches, 2 inches, and you have to figure out what is the distance. Remember, we're multiplying by distance, that's area, and then we have to do distance. So we want to say 4 inches plus 6 inches is 10, plus half of 2 is 11 inches. Alright, and there is A3. Switch colors again, and that is your sum of your areas times distance. Now we want to go to the sum divided by the sum of the areas only. And since we did all, the third was always the distance. That's the distance. That's the distance. We can just take, okay, 4 inches times 10 inches. We'll just take the first two of each. 4 times 10 plus 1 inch times 6 inches plus 6 inches times 2 inches. Since I set it up like that, I always did, you know, height or width times length times distance, width times length times distance, width times length times distance. Then I did width times length, width times length, width times length. And let's get our handy calculator out. Now let's go ahead and bring it down here. Four times 10 times 2 plus 1 times 6 times 7 plus 6 times 2 times 11 equals 254, and that divided by parentheses 4 times 10 plus 1 times 6 plus 6 times 2. And the total answers is 4.38, and that is inches. And if you look at your units, you're getting inch times inch times inch is inch cubed plus inch cubed plus inch cubed is going to be inch cubed, and you're dividing it by inch times inch is inch squared. So you're essentially dividing inch cubed by inch squared equals inches. And there you go. We'll go ahead and check and see if that's what they got. And what he does in the example is he makes a table, and I recommend doing this if you can at the beginning to kind of get used to it. In time, you'll get used to not doing it, but initially it's a good idea. And when looking at the example, he has 4.38, so we are right on. I don't believe in this example he goes ahead and solves for the moment of inertia, but we're going to anyways. And when you look at a moment of inertia for let's move down here. Moment of inertia typically will equal base times height cubed over 12, and this is for square sections. For square sections, base times height cubed divided by 12, and typically in the front of a materials, mechanics of materials type book, or maybe some other different structural books, you'll have equations for other type of shapes, but for, you know, I sections or certain types of sections like that, you can actually use this equation plus BH cubed over 12, and that'll tell you if it's just one section. You can say, oh, BH cubed over 12 is this, if you know where the neutral axis is, and it's actually symmetrical about the neutral axis. But if it's not, you have to do BH cubed over 12 plus 80 squared, and this is base of the rectangle times height of the rectangle divided by 12 plus the area of the rectangle times d is the distance to the neutral axis squared. And we'll go ahead and solve for, so we'll come on down here and we'll go ahead and solve for I of this shape. And he doesn't, once again, he doesn't do this in the example, but I'm going to do it just because I believe practice makes perfect, and the more you're going to do, the better you're going to get. So repetition, repetition, repetition. Alright, anyways, B. So let's do it the same way. We do A, 1. Well, we know, go ahead and put in the neutral axis here, or the centroid. So we know the distance to the centroid equals 4.38 from x there. So this is your neutral axis. You have to take, this is where the d comes, and I see in the next example he actually says it's y prime, I think is what he calls it. I've always called it d. So it doesn't matter. You'll find out in engineering there's a lot of different things they call different variables they use for different things. So you kind of have to define everything at the beginning of a chapter, or just use things that people use quite often. So d or y doesn't matter. Okay, so we'll go ahead and start with A. And these can get quite long, so we might get a little bit nasty here. So the base is 10. The height is 4. And that's BH cubed over 12 plus A, which is 10 times 4. D, which is 4.38 A, and then that's minus what? So if that's 4.38, we know that's 4, so it's 0.38, so it's going to be 2.38. 2.38 total, right? Let's get rid of this. Total is going to be 2.38, because right here you're going to have 0.38, and then you're going to have 2, so the total is 2.38 inches cubed. No, that's squared. AD squared. And then we're going to keep on going. So that's your A1 component of it. A2 component of it is B, which is 1 inch. H, 6 inch cubed over 12 plus AD squared. Shoot, you don't want to write A, you want to actually do A. Is 1 inch. 6 inches is your area. AD, and then D is what? Well, if it's you have 6 inches, and this is 4 inches, 4.38 inches down, so that's 0.38 inches into it. So it'd be 6 minus 3 minus 0.38 is what? It's 2.62. And I'm probably going to run out of time here, so that's why I'm trying to go a little bit quick. And we'll do it some more over the next couple problems. So I hope I'm not losing you here, but base is 6 inches. 2 inches is height, cubed over 12, plus AD squared. Your A is 6 inches times 2 inches, which is area. D, well, we figured that from the neutral axis, we know it's, well, this is 4.38, so it's 0.38, so that's 6 minus 0.38, so let's try it again, minus 0.38, plus 1 inch, 6.62 inches from the neutral axis, meaning the center of this section, this, equals 6.62 is what I'm calculating. I hope it's right. So calculate yourself. Don't agree with me. Look at it and double check me. I am not infallible. And we're going to go ahead and do this calculation here. When I do this big calculation, I get 869 inches to the fourth, and you'll see that it's inches to the fourth because we have to figure out where you're adding. You can cancel right here. This over here is inches times inches to the third, so that's inches to the fourth, plus inches times inches squared is inches to the fourth. Okay, we're good. So everything's inches to the fourth. And inches to the fourth is obviously not the most obvious thing, but what it's saying is area and how far away is that area. So the more area we have further away from the neutral axis, the more I you're going to have. So this is very good for moment problems. and moment issues.